Good morning, everyone. This is day 2 of our thermochemistry unit, and in this video we're going to kind of continue our discussion on heat and energy. And so one thing that I realized in yesterday's video that we didn't quite cover, maybe to the extent that you'll need to understand, is exactly what energy is and the types. So we did talk about this yesterday, that energy is the ability to do work or to produce heat. And we mentioned how this doing work part, that's more what you're going to learn in physics, but the producing heat part is really what we're going to talk about in chemistry. And so there are two types of energy. There's potential energy and kinetic energy. Now in chemistry we talk about chemical potential energy, which is the energy that is stored in the bonds of atoms. And if you are doing your vocabulary assignment, you're going to want to make sure that you get this vocabulary word down. The definition of kinetic energy, which you should remember from our conversations in class, is energy due to movement of the atoms. So that means the atoms are moving fast or slow depending on how much kinetic energy they have. So the more kinetic energy you have, the higher everything is moving. So if we look at solids, liquids, and gases, one thing that's interesting about solids, you notice all of these red atoms are closely packed together, and they really just vibrate in place. So that's what these lines mean, is they vibrate, which means they're moving very slowly. So this means that they have low kinetic energy, which we abbreviate as Ke. So kinetic energy is Ke, potential energy is Pe. Not physical education like your gym class, but Pe. Now liquids are spread further apart, but they're still connected and they flow kind of in the same direction, which it looks like one of my red atoms got deleted. And so you'll see that I'm drawing all the arrows pointing in the same direction. So they can flow, they can move, okay, but they're all still connected. And so these are going to kind of have like a medium amount of kinetic energy compared to solids. Now gases, they are really spread out, which I'm going to draw a little better here. I'm going to really spread them out. And the thing is they move quickly and in all kinds of random directions. There is no rhyme or reason as to how they move, but they move all around, and so they have a high kinetic energy. And this is when they're all at the same temperature. So if you have a solid, a liquid, and a gas at the same temperature, so let's go ahead and write that off on the side. So at the same temperature, then these ways of classifying their amount of kinetic energy is true. But the key thing, though, is what does temperature measure? A lot of you would say that temperature measures how hot or cold something is. But heat is really energy, and energy causes the atoms to move. And so temperature actually measures the average kinetic energy. So the average kinetic energy of the atoms. So that means the higher the temperature, the faster they're moving. So if we look at this question here, it says which compound has atoms with the highest kinetic energy? Well, we have object 1 that's at 25 degrees Celsius and object number 2 that's at 50 degrees Celsius. So go ahead and pause the video and decide what you think. Okay, so if you chose object 2, then you are correct. Because this has a higher temperature, 50 degrees is higher than 25 degrees, it is going to have a higher kinetic energy. So if you increase your temperature, that means you increase your kinetic energy. Now, one thing that I want to make sure we're clear on when we're talking about energy and heat specifically is how it relates to our first video. So remember, heat is going to travel. Okay, we measure the temperature really measures the movement and change in heat. And so for an endothermic reaction, heat is going to be traveling into your system. So if this box is our system and everything else around it is the surroundings, then we can see that heat travels from the surroundings into the system. So this means that the system is absorbing heat. And so what you should see is that your systems, the temperature will begin to increase in your system, whereas the temperature of your surroundings will decrease. So this, for example, would be like standing near a fire or holding on to a piece of ice. If you put your hand around a piece of ice, your hand is going to start to feel cold, but the ice is going to start heating up because your hand is transferring energy from your hand to the ice, and the ice is absorbing it and increasing its temperature. But in an exothermic reaction, the system already has a high temperature, or it might not, but whatever it is, it's getting colder because it's now releasing energy into the surroundings. And so this means that our system, if we just write it out again, is just releasing energy to the surroundings, and that could be literally whatever is around it. And if you're wondering, okay, well, what's the system? The system could be your test tube. It could be just whatever object it is. It could be your house, right? You could talk about how your air conditioning and heating unit in your house or your apartment works. Your system is whatever you are studying, and the surroundings is literally everything else in the entire universe. So keep this in mind when we're talking about kinetic energy and heat and temperature as we continue to move on. So with that, okay, remember thermochemistry, we said thermo means heat. So here, when we talk about thermal energy, we're talking about the energy related to heat. And energy is measured in joules. It's named for James Prescott Joule, which is why it's not spelled the same as like a diamond or an emerald. It's not that kind of joule. This is an old guy's last name, and the abbreviation is a capital letter J. And there are some conversions just to keep in mind. If you have 1,000 joules, that's going to be equal to 1 kilojoule. So that's a lowercase k and a capital J for kilojoules. And then if you have 4.184 joules, that's equal to 1 calorie. Now, one thing to keep in mind is that these are both lowercase c's. So those are lowercase. And there's a big reason why it being lowercase is important is because a 1,000 lowercase capital C calories is equal to 1 capital C calorie. And that's kind of confusing. And you might be like, why is the only difference between these two a capital and a lowercase c? And this is because a capital letter C is called a nutritional calorie. And it's used to measure the energy that's in your food. So if you go and you look at like a label for nutrition facts or nutritional facts, like on your container, it'll tell you like you have 100 calories, and however many servings you have. And you'll notice that's a capital C there. So it's talking about this. So if you're, for example, if you have a bag of Doritos, for example, and the whole bag of Doritos has 500 capital C calories in it, in the whole bag. Not just in the serving, just the whole bag. Well, you could say, okay, we have 500 capital C calories, and you could do a little dimensional analysis, and you could say, okay, 1 capital C calorie is equal to 1,000 lowercase c calories, and 1 lowercase c calorie is equal to 4.184 joules of energy. And you could do that math there to figure out how many joules of energy is actually produced. And this is not really a calculation that I'm going to ask you to do on a quiz or test, but it's something to keep in mind. So in this case, that would be 2092000. So 2,092,000 joules of energy. And so one reason why we use nutritional calories is so that you don't see that huge number on the back of your Doritos bag, because I don't think that would make anyone feel good to see that. But keep in mind, your doctors and things like that base, if you see a 2,000 calorie diet or whatever, you're counting capital C calories, not lowercase c calories. So it's all good there. Now, when we talk about, so we've talked about the units that energy is measured in, and what temperature really means, that it's the average kinetic energy, and what that looks like with solids, liquids, and gases. And so a key concept here, which you kind of already know just from your personal experiences, is that all materials are going to interact with heat differently. And objects, I'm going to zoom in on this here, an object's specific heat capacity, specific heat capacity, or capital letter C, the specific heat capacity is a measure of how many joules of energy are required to heat 1 gram by 1 degree Celsius. And if you are doing your vocabulary, you're going to want to make sure to get that vocabulary word down. That's one of them on your sheet. So again, specific heat capacity has the symbol capital C. So not for calorie. Capital C is your specific heat capacity. And it's basically saying, okay, how much energy do I have to absorb in order to change by 1 degree Celsius? So every time, so for aluminum, for example, it's 0.904 joules per grams degree Celsius, meaning that if you have aluminum here, and it's at 0 degrees Celsius. Every time you want to increase and heat it up, you have to use 0.904 joules of energy in order to heat it up. And so you can calculate how much energy you would actually have to use. Now, this is only if you have 1 gram, because we know that if you have a swimming pool full of water, or you have just a little coffee cup full of water for tea or something, which one is going to take longer to heat up? Well, we know the pool is, because even though the coffee cup is going to have the specific heat capacity is 4.184 joules per grams degree Celsius, and that would be the same for the coffee cup or for the water, but because the mass of the water is so much bigger in the pool than it is in the cup, the swimming pool is going to take longer to heat up. And so with this, it also means that, for example, if the sun is giving off 500 joules of energy, right? It's exothermic, it's releasing heat into the environment. But if we look at our car, you could have a seatbelt in your car, right? We've all experienced that, getting in your car when your car's been sitting in. And let's say you left a little, you left a water bottle in here while you, I don't know, went into school or something. If you think about it, by the time you get back, which one is going to have be hotter, have a greater change in temperature? And that would be the seatbelt. Because if the seatbelt is made of aluminum, which it's not, but the seatbelt is metal, and it's going to have a specific heat capacity similar to aluminum, very small, but water has a specific heat capacity of 4.184. It's almost 400 times strong, not 400 times, excuse me, 10 times stronger than the aluminum. And so that means for every degree it requires 10 times more energy to increase that water. So when you get back, your seatbelt is going to really hurt. If you accidentally touch it with your elbow or something like that, but the water is going to be just like, maybe it's really warm, but it's not even boiling or anything like that. So let's just take a look at this last question before we end this video. So which compound will experience the largest change in temperature when 5,000 joules of energy is absorbed? So why don't you go ahead and pause this video and decide which one, A through E, is going to experience the largest change in temperature when 5,000 joules of energy is absorbed. Okay, so what you should have chosen is the one that's going to experience the largest is glass. Okay, and this is because it has a smaller specific heat capacity than all the other ones. So a small specific heat equals a large change in temperature. And that's because you do not need a lot of energy in order to change by every degree. Whereas if you were looking at paraffin here, a large specific heat means that it would have the smallest change in temperature. So I hope that you have learned some things, that your notes match what's on the screen, okay? Don't try to summarize this. You get to use these notes on your quizzes and tests, so make them good. And if you have questions, go ahead and join the Zoom call later today for it. And you remember, use your notes for your quizzes and tests. Have a good day, guys.